So we've reached the point in our class where we kind of, I don't know, I don't want to say we stopped learning new things, but we kind of stopped learning new things. We kind of shift our focus from trying to learn how to take derivatives of new functions to trying to use all that knowledge that we've gained with various applications. So really what you'll see going forward, and you may have seen it in the last couple of sections, is that our goal is less to acquire new knowledge and more to apply knowledge that we already have. Understand how powerful the stuff that we've already learned is. In this section, we're going to use what we know about derivatives to talk about the shape of different graphs. And I guess that's interesting in its own right. Now that we understand derivatives, we have this new tool to analyze the different shapes of graphs if we just know the equation of the graph. But really the main purpose of that knowledge is not ending with just understanding the shapes of graphs. What we'll see is once we understand the shapes of graphs, there'll be a lot more applications of what we can do with these derivatives. But anyways, I guess we'll see all the applications as we go. For now, I just want to show you how derivatives affect the shape of graphs. And that's kind of interesting because we originally used graphs to come up with this whole idea of a derivative, right? We drew secant lines and then we let the 2 points that define the secant lines get really close together. And that introduced this thing called the tangent line. And that idea gave way to limits and helped us understand our definition of the derivative formula, where we evaluate the limit of the difference quotient. The basis of all the stuff we learned in calculus kind of came from this formula, and this formula kind of came from looking at graphs and taking 2 points and letting them get arbitrarily close together. Our algebra all started with the graphs, and now we're taking all that knowledge we have of the algebra and applying it back to graphs. That's a lot of talking. Let me show you an example. Suppose we consider the graph of f of x equals x times the sine of x, which is pictured down here. It's kind of a cool looking graph. But what I want you to do is pretend we didn't have this graph at all. But we're still interested in studying the behavior of this function around the point where x equals pi over 2. So right over here on my picture. What could we do if we wanted to understand the graph at this point? Well, probably the first thing we'd do is we'd figure out what is the height of the graph at that point. What is f of pi over 2? And that's easy enough to figure out. It doesn't involve any calculus at all. We just copy the formula that we have written here, changing all the x's into pi over 2's. So f of pi over 2 would be pi over 2 times the sine of pi over 2. And depending on how well you have your unit circle memorized, you may or may not know that the sine of pi over 2 is just equal to 1. So this is pi over 2 times 1, aka pi over 2. The height of this graph in red when the x value equals pi over 2 is some number somewhere in here. It appears to be between 1 and 2, which makes sense. Turns out it's exactly equal to pi over 2. That's cool, but it's got nothing to do with calculus. In calculus, we move beyond just understanding the height of the graph and realize that there's more important features if we want to study this graph where x equals pi over 2 than just the height of the graph. For example, we might be interested in the rate of change of the height of the graph. If my input's a little bit more than pi over 2 or a little bit less than pi over 2, is the new height of the graph going to be a little bit more or a little bit less than the height was at pi over 2? Well, those are all things we can understand if we understand the slope of the tangent line to the curve at this point. In other words, the derivative of this function evaluated at pi over 2. Since f of x is sine of x, we can figure out f prime of x by just taking the derivative of x times sine of x. Maybe you'd recognize that we have a product rule going on here. So you take the derivative of the first thing and then multiply that by the second thing, and then add to that the derivative of the second thing multiplied by the first thing. You may be at the point where you don't even need to write these steps out. You can just see that the derivative of x is going to end up being 1. So you'll have 1 times sine of x. In other words, sine of x is your first term. And since the derivative of sine of x is cosine of x, you'll have x cosine of x as your second term. Because f prime of x is equal to the sine of x plus x times the cosine of x, I can evaluate f prime of pi over 2. It would just be the sine of pi over 2 plus pi over 2 times the cosine of pi over 2. And again, if you have your unit circle memorized, maybe this is something you can figure out. The cosine of pi over 2 is just equal to 0. So my second term here is just going to be equal to 0. So the entire thing is just going to be equal to the first term, the sine of pi over 2, which is equal to 1. What I'm saying is f prime of pi over 2 is just equal to 1. What does that mean? It means if I were to draw the tangent line to this curve at this point, that line would have a slope of 1, which is what this line in blue appears to have. By looking at f of pi over 2, we figure out the height of the graph when x is pi over 2. By looking at f prime of pi over 2, we learn about the slope of the tangent line to the graph when x is equal to pi over 2. And now we have a lot of information about the graph. But we don't have to stop there. Really, the reason that we figured out this tangent line right here is it gives us information about what happens to the graph when I'm a little bit more than pi over 2 or a little bit less than pi over 2. If my x value is a little bit more than pi over 2, because the slope of this tangent line is positive, the height of the graph will be a little bit more than the height of the graph was at pi over 2. And similarly, if my x value is a little bit less than pi over 2, the height of the graph is going to be a little bit less than the height of the graph was when x equals pi over 2. The derivative tells us about the rate of change of the graph, which is a really important characteristic, but it only tells you about the rate of change of the graph at that instant. What if you're interested in the rate of change of the graph at points a little bit more than pi over 2 or a little bit less than pi over 2? Put differently, what if you're interested in how the slope of the tangent line to this curve changes when your x value is a little bit more than pi over 2 and a little bit less than pi over 2? The slope of the tangent line represents the change in the graph. We're interested in the change in the slope of the tangent line. In other words, the change in the graph. What I'm trying to describe is the second derivative of this function. Algebraically, it's easy enough to figure out the second derivative because we know the first derivative. Since the first derivative is the sine of x plus x times the cosine of x, the second derivative would be the derivative of the sine of x plus x times the cosine of x. And anytime we're taking the derivative of a sum, we can just take the derivative of each of the terms individually. So the second derivative would be equal to the derivative of sine of x plus the derivative of x times the cosine of x. Fortunately, these are both things that we can figure out. The derivative of sine of x is just equal to cosine of x, and to figure out the derivative of x times cosine of x, we use the product rule, which tells us that we have to take the derivative of the first thing, x in this case, and multiply that by the second thing, the cosine of x, and then we add to that the derivative of the second thing, the derivative of cosine of x, the first thing, the x. The derivative of this x is just equal to 1, and the derivative of this cosine is equal to negative sine of x. So when all the dust settles, we got the cosine of x as our first term. We have 1 times the cosine of x, in other words, the cosine of x is our second term. And we have negative sine of x times x, in other words, negative x sine of x as our third term. We could rewrite this as 2 cosine of x minus x sine of x, and we have a simplified version of our second derivative. Now that we know our second derivative, we can evaluate it at pi over 2 by copying exactly what we see here, except changing all the x's into pi over 2's. We get 2 times the cosine of pi over 2 minus pi over 2 times the sine of pi over 2. Due to the fact that the cosine of pi over 2 just equals 0, this is going to simplify really nicely. This entire term is going to go away. The sine of pi over 2 is just equal to 1, so I got negative pi over 2 times 1. In other words, negative pi over 2. It's hard to make much sense of what this value means, but the important fact will be that this is less than 0. What does that mean? The fact that our second derivative is less than 0 means that as our x value changes, as we're reading this thing from left to right, our first derivative is decreasing. Wait, can you draw me a picture of that? Yeah, absolutely. It's a little hard to see, but if I pick a point slightly to the right of pi over 2, which is represented by this little pink dot right here, and I draw the tangent line to the curve at this point, it produces this line in pink. And then if I go a little bit further to the right, represented by this purple dot, and draw the tangent line to the curve at this point, it's represented by this line in purple. Think about the slopes of the line pictured in blue, pink, and purple, which come from the points in green, pink, and purple respectively. The slope in blue is equal to 1. We already calculated that. The slope in pink, it's still some positive number, but it's less than 1. I don't know, maybe like a half or something. And the slope in purple, that's damn near 0. I mean, I guess it's barely increasing, but it's almost horizontal. The point is the slope is going from 1 to roughly 1/2 to roughly 0 as I go to the right. The slope of these tangent lines is decreasing. The change in the first derivative is negative. That's why my second derivative is less than 0 here. We can keep going. We can calculate the third derivative, which would be the change in the second derivative, or the fourth derivative, which would be the change in the third derivative. But once you get beyond the second derivative, it's pretty hard to make sense of what your analysis is even telling you. For the purposes of our class, we'll be very interested in the height of the function at a given point, the slope of the tangent line to the function at a given point, which is represented by the first derivative, and the change in the slope of the tangent line at a given point, which is represented by the second derivative. It's a lot to keep straight, but I think once we introduce some vocabulary, it'll be a lot easier to understand. We already know how to analyze the height of the function at a given point. That's all pre-calculus stuff. It's the first and second derivative where I want to introduce vocabulary words. And here they are. Anytime your first derivative at a given x value is greater than 0, that means your function is increasing. That word makes a lot of sense, right? The fact that this line in blue has a positive slope means that the little person hiking along this red path right here is going uphill at pi over 2, this point pictured in green. This person is still going uphill at this point pictured in pink, and this person is ever so slightly going uphill at this point in purple. But if I considered what was going on when this person was at an x value of pi, this point pictured in brown, now the person's definitely going downhill. The function is no longer increasing, it's now decreasing. When the first derivative is greater than 0, our function is increasing. When the first derivative is less than 0, our function is decreasing. Think going uphill as you walk from left to right, or going downhill when you walk from left to right. Those are probably ideas you already understood going into this section. But a couple of ideas that you may not have been familiar with coming into this section are the ideas of concavity. When we look at the second derivative, if our second derivative is greater than 0, we say that our function is concave up. And if our second derivative is less than 0, we say our function is concave down. For concave up, think like a bowl, like a cereal bowl or something. Something that has this shape is concave up, whereas something that is concave down, think like an upside down cereal bowl. Something that has this shape, loosely speaking. The way to think about this is at any point in here, we can talk about the slope, which would represent the first derivative. So I could sketch the tangent line at this point, or at this point, or at this point, and so on. And if you look at what happens to the tangent lines at these various points as I go from left to right, what you'll see is the slope of the tangent lines is increasing. I'm not saying the function is increasing. Sometimes the function is increasing, sometimes the function is decreasing. But the slopes are increasing. The slope right here is some large negative number. Here it's still negative, but not quite as large. Still negative, but now it's getting pretty close to 0, really close to 0. Now it's right around 0. Now it's slightly positive. Even more positive, even more positive, even more positive. It's going from a large negative number all the way down to a small negative number to 0 to a small positive to a large positive. It's increasing as you go from left to right. Not the function, but the slope of the tangent line is increasing. When the slope of the tangent line is increasing, your function is concave up. And the exact same logic works down here for concave down. If you look at the slope of various tangent lines along this curve, what you'll see are those slopes are decreasing. I'm not saying the function is decreasing. The function's only decreasing on the right half here, but the slopes of various tangent lines are decreasing. Here's a little grid that might help you keep this stuff all straight. Your function can either be increasing or decreasing. To figure out which it is, we have to evaluate the first derivative. Similarly, your function can either be concave up or concave down. And to understand which it is, we need to analyze the second derivative. A function that is both increasing and concave up would look like this. It's going up as I read it from left to right, the hiker is going uphill, and as I go from left to right, it's getting steeper and steeper and steeper. What would it look like to be increasing and concave down? Well, I'd still want to be going up as I go from left to right, but the rate at which I'm going up would have to be going down. So this hiker would start out on the really steep part, and it would get easier and easier as he goes, whereas this hiker would start out on the easy part and it gets harder and harder as they go. We can do the same thing with decreasing. What would it look like to be decreasing and concave up? This hiker is going downhill as they go from left to right, but the slope is getting bigger, meaning less and less negative as they go from left to right. So decreasing and concave up would kind of look like this. We're always going downhill from left to right, but right here our slope is, -5, and here it's only -1, and then it's -1/2, and then -1/4. Those numbers are getting bigger and bigger, aka closer to 0, less and less negative. What about decreasing and concave down? Well, loosely speaking, that's going to look like this. As we go from left to right, we're going downhill, but the rate that we're going downhill is getting less and less, meaning more and more negative. The slope here is, -1/2. The slope here is, -10 or something. If you can make sense of this grid and understand these 4 different shapes, you have a pretty solid understanding of how the first and second derivative affects the shapes of the graphs. The kind of practical application of this, which is typically quoted, is if your function gives you position, then f prime gives you the velocity, the change in position, and f double prime gives you the acceleration. The change in velocity is your acceleration. If you used to be driving 10 miles per hour and now you're driving 20 miles per hour, your velocity changed, you accelerated. Thinking in terms of this context, instead of saying when the first derivative is greater than 0, we're increasing, we could say when the first derivative is greater than 0, our velocity is positive, we're moving forward. Whereas when the first derivative is less than 0, our velocity is negative, kind of backing up if you want. And when your second derivative is greater than 0, you're accelerating. And when your second derivative is less than 0, you're decelerating. When your velocity is increasing, you're accelerating. When your velocity is decreasing, you're decelerating. One more bit of vocabulary I want to give you before I end this video. So far, we've only talked about greater than and less than 0 for the first and second derivative. But what about when the first derivative is equal to 0? Or when the second derivative is equal to 0? Do I have any fancy names like I do here for those points? Turns out you do. When the first derivative changes sign, which typically happens when the first derivative equals 0, but what we'll see in the future is there's other cases where our first derivative can change sign. But the most important ones for our purpose is when the first derivative is equal to 0. Those are going to be called critical points. And as the name suggests, they're going to be super important. What about the second derivative where that changes sign? Well, typically it happens when the second derivative equals 0, right? Because if you're kind of going from positive to negative, you're going to cross over a 0, loosely speaking. Those points are called inflection points. Critical points and inflection points are really important, and it'd be nice if you could locate those on the graph, and that's what we're going to start the next video with.